Hi, my name is Taran Agnihotri, and today I'll be presenting Lab 5, Friction. The problem we're trying to solve is to find the coefficient of kinetic friction. Theoretically, if we know the initial speed of an object and the distance and time it takes to stop, we can calculate the force on it. If the only unbalanced force is friction, we can then calculate the frictional force and the coefficient of friction. This is made possible by Newton's second law of motion, which originally says acceleration is equal to F net divided by mass, and it can be rewritten as F net equals mass times acceleration, and the friction formula, which is force of friction equals coefficient of friction times mass times gravity. For our experiment, we have a power bank of 0.16 meters in length and 0.19 kilograms slid across the desk. The camera was mounted above the desk and under bed in a stationary position. Tracker was used to analyze motion, and Google Sheets was used to make graphs. We have some assumptions in doing this lab. The first is the table is level. The second is the camera lens is not distorted. Third, the sum of net force after the ball is released is only the force of friction. Fourth, the error is negligible. And fifth, all measurements taken are accurate. For our tracker model, we started at frame 20 and ended at frame 40. This meant we analyzed 20 frames total, and the frame dt being 0.033 seconds, we analyzed 2/3 of a second total. It was calibrated with the length of the power bank of 0.106 meters, and the axis was centered at the power bank with the x-axis going right. Here's our tracker recording. Here's the tracker data laid out. Here's the tracker data in a graph form, making it easy to see. Here are the velocity calculations. So for this I use v equals delta r over delta t, and with our initial velocity calculations, and we found the initial velocity to be 1.136 meters per second. For the force calculation, we use a final velocity of 0 meters per second, as that's when the power bank was at rest, and an initial velocity of 1.136 meters per second. The mass, as stated previously, was 0.19 kilograms, and the delta t was 0.633 seconds. This gave us a net force of negative 0.341 newtons, which meant our force of friction was negative 0.341 newtons. To find the coefficient of kinetic friction, we use a friction formula with the force of friction as 0.341 newtons, our mass, same as before, is 0.19 kilograms, and the force of gravity as 9.81 meters per second squared. And that gave us a mu of 0.183. So here are the total results. The mass was 0.19 kilograms, initial velocity is what we calculated earlier, the final velocity is 0 at rest, the delta t was 0.633 seconds. This gave us a force of friction of negative 0.34100 newtons, and a coefficient of kinetic friction of 0.183. Now in this lab there are a few error sources which can be accounted for. Uneven table. The table, although it was even as possible, was not perfectly level, and this could have led to some inaccuracies in the calculations. Second of all, the surface was not perfectly smooth. Imperfections in the surface not only lead to friction, but other inaccuracies that could have affected our calculations. The third, and probably the most major of the error sources, were the hand-picked points. In Tracker, as all the points were picked by hand, they could be inaccurate and did not show the true center of mass. And fourth, this problem we can't do anything about, but we can only be aware that around the edges there's some slight camber distortion. Overall, if we know the initial and final velocities of an object, and the time between those two velocities, we can find the acceleration on an object. We can then use this acceleration combined with the mass of an object to find the net force on an object through Newton's second law. This is F net equals mass times acceleration. Through this, we can accurately calculate the force of friction on an object, as well as the coefficient of friction, allowing us to accurately predict motion of objects. Thank you.